Hello there, welcome back to Thermodynamics. We are still in chapter 5, this time part 3 of chapter 5. So within this knowledge clip, I will tell you a little about chemical reactions at equilibrium. We'll find out what that means, and then I also show you how the equilibrium can be manipulated by coupling chemical reactions. So let's get started. Let me begin by defining the general chemical reaction equation. It looks as follows. We have a reactant A and a reactant B. They react together to form product C and D. As usual, each reactant has their respective stoichiometric coefficient, which here is abbreviated as nu for reactant A, nu A, for reactant B, nu B, and so on for C and D. Now, maybe you notice there's one difference compared to how we wrote a chemical reaction previously, which are these double arrows. Those double arrows indicate that this is a chemical reaction that is at an equilibrium state. We will find out what that means in the following. So, how do we calculate the Gibbs free energy change when we go from reactants A and B to products C and D? It's given as follows. We do this for a constant pressure P and a constant temperature T, so that the dP and the dt term can be cancelled from the definition of the free energy change. So we've seen that earlier. We take the partial derivative of the free energy with respect to the change of moles of reactant A and multiply that with the change of moles of reactant A. As simple as that. And the same goes for the partial derivative of the free energy with respect to the moles of reactant B. As the reaction proceeds, right, A and B will react. Their mole numbers will change, which is indicated by the dNA and dNB variables. And the same goes for the products. The Gibbs free energy will also change with respect to the amount of moles of product C, for instance. So usually, if we start with pure reactants, the amount of products over time will increase. So dNC will be a positive number because it increases. And now the question is, how does the Gibbs free energy change with an increasing amount of reactant C, which is given by the partial derivative? And of course, also for reactant D, we need to ask, how does the Gibbs free energy G change when product D is formed, which is given by the partial derivative? Okay, and last class we saw that those partial derivatives of the Gibbs free energy with respect to the amount of moles that are added or taken out of the systems are given by the so-called chemical potentials of the corresponding species. There's a chemical potential for reactant A, one for reactant B, and for the product C and D. There are always individual chemical potentials that define how the free energy changes with adding more or removing the components. Good. So with this in mind, let's define the so-called reaction progress variable. This Greek symbol, I always forget its name. Let's just call it squiggle because it has such a nice curve at the bottom, or two. So what does that reaction progress variable mean? If this squiggle is 0, that basically means that no reaction has occurred at all. Everything is still pure reactants A and B. On the other hand, if squiggle is 1, that means that all reactants have converted to the products, right? So squiggle can range from 0 to 1, simply. That's kind of counting the progress of the reaction, okay? So with this squiggle, we can now express the changing moles of the reactants and products in a different way. We can write the stoichiometric coefficient of the corresponding reactant times the change of that squiggle variable, right? And since reactant A is depleted during the reaction, we put a negative sign in front of the stoichiometric coefficient, right? And the same we do for reactant B. We also multiply the stoichiometric coefficient with the change of that squiggle parameter and put a negative sign to account for that reactant B will also decrease as products are formed. But for the products, on the other hand, like C, we actually put a positive sign in front of the stoichiometric coefficient because the amount of products will increase as squiggle goes from 0 to 1, right? For C as well as for D, right? So since squiggle, our reaction progress variable, is always a positive number between 0 and 1, we have to introduce these signs here to account for whether it's a reactant or product, right? Okay, now with this definition, let me express this change of the free energy here with the squiggle parameter, or the change of the squiggle parameter, which I do here. Again, the change of the free energy at constant pressure and temperature is now, I put all the chemical potentials and of the corresponding reactants and products, as well as their stoichiometric coefficients, into this parenthesis here and multiply it with the change of the squiggle parameter. So you see I plugged in these expressions for the different amount of moles, the change of the moles, and then factored out the change of the squiggle parameter, right? Okay. Let's hold on to this definition for a moment. Okay, now I'm just going to divide the free energy change with the change of the squiggle parameter. And for simplicity, I leave away the P and T being constant. We know this from the previous equation. And then all that is left on the right side of that equation is the expression in the parentheses with the stoichiometric coefficients and the chemical potentials. Okay, let me plot the free energy now, independence of the squiggle parameter. I do this in this box here. So on the y-axis, I write the free energy, and on the x-axis, the reaction progress parameter squiggle. And now I draw the dependence of G on squiggle. Here it comes. So it's this typical U kind of shaped curve. And now we have 3 points that we can look at. The first one on the left here. So that point is where that value for the slope of the free energy with respect to the reaction progress is negative, right? That tangent that we draw here, which is the derivative of the function here at that point, is negative. It has a negative slope. It goes down here. That means we're going in the right direction towards a spontaneous change for the reaction, right? If the reaction progress parameter is located here, then we are at a position where there can still be more reaction proceeding so that we move towards a lower free energy. Okay? And on the other hand, that point here the slope of the free energy with respect to the reaction progress squiggle is positive, right? So that indicates that here we don't go to the right, but we go to the left. So we are actually now at a state where more products have formed than you would have at equilibrium, and therefore the reaction would produce again reactants actually rather than products, because the equilibrium of the reaction, that is down here where the free energy with change with respect to the reaction progress parameter, where that slope is 0. That's the equilibrium point for a chemical reaction, right? So at equilibrium, the free energy change with respect to the reaction progress change is 0, simply. That's the condition for equilibrium, so that the reaction does not proceed anymore. So now, if that's true, then this entire expression here must be 0, and then we can move the negative terms on the left-hand side of the equation, and the positive terms we leave on the right side. Then those two expressions must be the same. Important insight. So generally we can write that the multiplication of the stoichiometric coefficients and the chemical potentials of the corresponding reactants, the sum of those for the reactants must equal the sum of the same multiplication of stoichiometric coefficient and chemical potential for the products. Right? That's a condition that applies for at equilibrium. Okay. Okay, now that we have this expression here for how the chemical potentials of the reactants A and B connect to the chemical potentials of the products C and D, we can continue using this expression to arrive at a conclusion for the equilibrium, which is our goal here. So first what we do is we plug in expressions for the chemical potentials of A, B, C and D. And last class we learned how this can be done. We found that the chemical potential of component I can be expressed by the chemical potential of component I at standard conditions, right? Plus that term, that logarithmic term that gives the concentration dependence of the chemical potential. So that logarithmic term times the gas constant and the absolute temperature. That's the concentration dependence of the chemical potential that tells you how much the chemical potential is different from the standard state, basically. At the standard state, the concentration is usually 1 mole per liter, right? And that actually allows me to do a simplification in my expression for the chemical potential. And that simplification is actually not formally correct, which I will tell you now. So first, I simplify the expression of the chemical potential by not considering the standard concentration anymore. As you see here, standard chemical potential plus RT times the logarithm of only the actual concentration. And why can I do this? Because the standard concentration is usually 1 mole per liter. Because if now I plug in the concentration here, or here in moles per liter, and then divide by 1 mole per liter, right? Then the number doesn't change because I divide by 1. But it is not exactly correct, because it's actually a major sin to take a logarithm of a number that has a physical unit, like here mole per liter. That's not correct. Normally you can only take logarithms of numbers that have no unit, which is the case here, for instance, because the units of the concentration here and down there cancel each other out, but here they don't. And therefore this is not formally correct, but I still do it because I want to save myself some writing work, which the computer is anyway doing for me, as you already have noticed. So now I'm expressing the first term here with this expression, right? First, I write the stoichiometric coefficient, nu A, times the chemical potential at standard conditions, which is this part here, and then simply plus the stoichiometric coefficient times the concentration dependence of reactant A, which is given by this term. And the same thing for reactant B. First, again, the standard chemical potential coming from here, then plus the stoichiometric coefficient times the concentration dependence for reactant B. And of course, the same goes for the right side of the equation, where I now replace the chemical potential for reactant C, product C, with this expression, standard and concentration dependence. And no surprise, also the same thing for for product D. Good. Now let me further modify this slightly long expression here with an algebraic rule that is very handy. So that algebraic rule that I want to show you, you probably already know it, is that if you have an expression like this, where you have a logarithm and you multiply it with some numbers before the logarithm, then you can actually take those numbers into the exponent of the expression in the logarithm. In this case, I'm doing that for the stoichiometric coefficient nu a. Right? I move this nu a into the exponent inside of the logarithm expression. And I do the same for the stoichiometric coefficient of reactant B. Right? And now this is the first algebraic rule that I apply. The second algebraic rule is that I combine the two logarithms into one. So because these two expressions are added, I can combine the two logarithms by multiplying the expressions with each other inside of the logarithm, right? And then I factor out the RT, which is the same for both of these terms, and I end up with this expression, which looks sort of more simple than the first one here. Okay, and that's what I'm going to do now with these terms here. But first, I will bring all the standard chemical potential terms on one side of the equation, which I do here. First, I subtract on the right side from nu c times mu c standard, nu a times mu a standard, and nu b times mu b standard. Right? I simply brought this term and that term onto the other side. Okay, and now comes this algebraic trick here. On the right side now, I combine the logarithmic expressions with each other to obtain a single logarithm. And for those parts that are negative, so instead of when I don't do addition but subtraction, there is a division. And then I also put a negative sign in front of this expression, which turns around actually the numerator and denominator in this expression. Okay, so I'm sure you can follow this. Now we have that expression, and that's a fundamentally important definition, which I show you in the next slide. So what this formula teaches us is that here the left side is only composed of chemical potentials at standard states. So this expression actually corresponds to the Gibbs free energy change at standard conditions. The right side here is this logarithmic expression, and the part in the natural logarithm is the concentration dependence at equilibrium, right? It relates the concentrations of reactants and products to each other at equilibrium, where the free energy is minimum. And that relationship is called the equilibrium constant, simply, right? So this expression is so fundamental, it allows us to generalize for all possible biochemical equilibria. We can always say that the sum of the chemical potentials at standard states of products minus the chemical potentials at standard states of the reactants, that subtraction equals the expression on the right side, which is minus RT times ln K. So more simply written, this free energy change at standard conditions equals this logarithmic dependence on the equilibrium constant. So the equilibrium constant tells us what the composition at equilibrium of reactants and products will be. Now we can rearrange this equation for the equilibrium constant. So first we divide delta G standard with minus RT, and then there's only ln K, and then we just take the exponent of both sides, and we get this expression for the equilibrium constant, which is e to the minus delta G standard divided by RT. So delta G standard, we've learned before, can be calculated with the Gibbs free energy changes of formation. You remember, with respect to the pure elements, carbon, hydrogen, oxygen, nitrogen, that is where the free energy change, the free energy is defined to be 0. And for any molecule, you can then obtain, with respect to that state, a free energy of formation. And those free energies of formations allow us to calculate the free energy change at standard conditions, which can then be used here, as you see. So we get the free energies of formations from tables, right? And then we plug the resulting value for the Gibbs free energy change at standard conditions into the exponent here, and then we simply get the equilibrium constant.